Hey everybody, it's Friday, March 19th, and as you can see here in the aim today, our goal for today's video is all about how we can use our understanding of linear momentum to describe angular momentum. Now, angular momentum is a pretty big and important topic in this course, particularly in the rotational motion unit. And so we're actually going to spend a bunch of days talking about angular momentum. Having said that, for today, we're really just going to focus on the basics. That means we're going to talk about what angular momentum is, what angular momentum's relationship to other rotational quantities is, and basically how we can use it to solve some problems. Now, of course, one of the main things we're going to talk about starting off is that every single rotational motion variable has a linear analog. And so, of course, as is suggested here by the aim, a lot of our understanding of angular momentum is going to come from our understanding of linear momentum. And so before we get into this here, we should just take a moment to remind ourselves of all the important things we said about linear momentum. The first thing we'll say here is that linear momentum is a measurement of how hard it is to stop an object. If an object has more momentum than another, all that means is it is harder to stop that object. Now, of course, because in order to stop an object, you need to apply a force on that object, there's a clear and very important relationship between momentum and force. As we said, since a force is needed to stop an object, we can also say that force is a measurement of the time rate of change of momentum. And if we put that in the form of an equation, it would look like that: F equals delta P over T. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so then what does that mean for angular momentum? It's obviously the big question here. Well, angular momentum is the rotational analog of linear momentum. And that really is true in the truest sense of what we mean by that. It literally just means what linear momentum means, but for rotation. So angular momentum, as best as we can define it, is a measurement of how hard it is to stop an object from rotating. That's it. Linear momentum is a measurement of how hard it is to stop an object from moving linearly. Angular momentum is a measurement of how hard it is to stop an object from moving angularly, or in other words, rotating. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So now what we want to do here is come up with an equation for angular momentum. And I want to be very clear about the point I feel like I've made pretty clear so far, which is that angular momentum is just the straight up rotational analog of linear momentum. That's really all that needs to be said about it. Remember, the equation for linear momentum is P equals mv. So as we've done for many other equations, all we really need to do here is just think of what is the rotational or angular analog for all of these variables. The rotational analog of mass, as we've said a bunch of times now, is the rotational inertia, I. The rotational analog of v, the linear speed, is omega, the angular speed. And that means the only other thing we need to put on this side of the equation is the symbol for angular momentum. And as it turns out, the symbol for angular momentum is L. So you can write this under the heading angular momentum. The symbol for angular momentum is uppercase L. The equation is L equals I omega, where I is the rotational inertia, given in units of kilogram meters squared, where omega is the angular velocity, measured in radians per second. Now, of course, you should be able to use this to figure out what the unit of angular momentum is going to be, and it's not all that complicated to figure out. The only thing you have to remember is that when we are combining units, when the radian is a part of one of the units, we have to treat it as a 1. So really, when you're multiplying kilogram meters squared times radians per second, the way you treat that is you're multiplying kilogram meters squared times 1 over seconds. And when you do that, that means the unit for the angular momentum, L, is a kilogram meter squared per second. Now, some of you might be thinking, why in the heck is angular momentum given the symbol L? It's very complicated. There was a lot of disagreement about the symbol to use for angular momentum. A bunch of different textbooks and different sources used a different symbol for a very long time, really until the 1960s. Ultimately, it was quantum mechanics that sort of forced the rest of physics to adopt the convention that L is the symbol for angular momentum. Honestly, don't go too nuts about why that's the symbol. It just is. So get over it. The quantity, of course, of angular momentum, like its linear counterpart momentum, is a vector. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, an important point that we should make about angular momentum is that it is a vector. And just like linear momentum, because linear momentum gets its direction from the direction of the vector it's based on, the velocity, the angular momentum has the same relationship to the angular velocity. The angular velocity vector determines the direction of the angular momentum. If the object is spinning counterclockwise, abbreviated CCW, the angular velocity is positive, and so is the angular momentum. If the object is spinning clockwise, CW, the angular velocity is negative, and so is the angular momentum. Just like was the case for linear momentum, the direction of the angular velocity determines the direction of the angular momentum. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I like this picture here. I think this is a pretty good picture. I like that it sort of summarizes every single thing that needs to be said about the relationship between angular momentum and linear momentum, the similarities mathematically, et cetera, et cetera, et cetera. But I think the most important thing about this diagram for you to remember is that just like angular velocity, the angular momentum has a direction which is perpendicular to the plane of rotation. So what I mean by that here specifically is that this object is rotating along this plane, but the angular momentum acts along this axle. Notice that's perpendicular here. And so the important thing to remember is that you really need to remember that right-hand rule for determining the direction of the angular velocity. If you take your fingers and you curl them in the direction of the rotation, notice that's up and over this cylinder. So you'd be curling your fingers like that. Then your thumb points to the left over here in this direction. And so the basic idea is, in exactly the same way that the fact that the velocity is in this direction means the linear momentum is in that direction, well, the fact that the angular velocity is this way means the angular momentum is that way as well. And so it's very important to remember here that the right-hand rule governs the directions of these vectors. And sometimes it's easier to just use it because otherwise you're going to have to remember a lot of stuff. It's really important to remember here, the angular momentum follows the angular velocity vector. And ultimately, while the right-hand rule is good for that, in a normal situation, which this is not really a normal situation, notice, because this axle is kind of like tilted and weird looking in this picture. If you're looking at the thing moving counterclockwise, the omega is positive and so is the angular momentum. And if it's rotating clockwise, both are negative. All right, now, before we move on to actually solving some problems here, we want to establish a clear and very important relationship first. And that important relationship is the relationship between the angular momentum and the torque. And so I'm going to talk about linear momentum here for a minute and its relationship to force, and then we can transition to talking about the relationship between angular momentum and torque. So we'll start by talking about the linear momentum, and I'll show that on the left-hand side here. Remember, linear momentum is given by the equation P equals mv. And so, of course, we have a pretty interesting question, and that's, well, how does that relate to force? Because obviously, if momentum is a measurement of how hard it is to stop an object, we want to know the relationship between the momentum and the force, because the force is the thing that is stopping the object. And so we start, and this will be mostly review for, I would imagine, most of you. We start with the relationship that F net equals ma. And we can say here that since F net equals ma, we can do some manipulating of this equation to say, well, instead of writing this in terms of the acceleration, because that's not in the momentum equation, we could write this in terms of the velocity. And so we can do that by writing the net force equals the mass times the change in velocity over time. And that's because A equals delta V over T. Now, to really sort of fit this into the mold of the momentum stuff, we recognize here that, well, m delta V is delta P. And so that leads us directly to this relationship between the force and the momentum, which is that the force is equal to the change in momentum over time, or that the force is equal to the time rate of change of momentum. Okay, well, just like we said a second ago here, the angular momentum is equal to I times omega, the rotational inertia, times the angular velocity. And so if we want to write an equation that relates the angular momentum to the thing that will be stopping the object from rotating, then we're going to have to write an equation that relates the angular momentum to the torque, because a torque will be stopping an object from rotating. And so the idea here is that just like we started with Newton's second law over here, we're going to start with Newton's second law for rotation over here, which is that the torque is equal to I alpha. And in just the same way that acceleration, linear acceleration, is equal to the change in linear velocity over time, well, we should remember from the beginning of this unit that the angular acceleration alpha is equal to the change in angular velocity, delta omega, over time. And the parallels here should be obvious. In exactly the same way that m delta v is delta p, because the mass of an object won't change, I delta omega is going to be the change in angular momentum, because an object's rotational inertia, assuming it's like a rigid solid object, is set. And so that means here that I delta omega is delta L. And so that means we can write our equation here as the net torque equals delta L over time. The torque is equal to the change in angular momentum over time. The torque is the angular momentum's rate of change. Now, we'll write that in more detail on subsequent slides here, but take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, way back when we first started talking about this equation in the momentum unit, I wrote this note for you in the PowerPoint. It said to change an object's momentum, you must apply a force, where F equals ma, which is equal to delta P over T. Because force is the time rate of change of momentum. And that's really super important because it helps us to reinterpret what a force means. When you look at a 10 Newton force, we used to think, well, a 10 Newton force is a kind of force that can make a 1 kilogram object have an acceleration of 10. And looking at it in the lens of momentum should make you think, well, a 10 Newton force is a force that can change an object's momentum by 10 kilogram meters per second per second. What we're saying here is exactly the same thing. To change an object's angular momentum, you must apply a torque, where the torque is equal to RF sine theta, which of course is going to be equal here to delta L over T, because torque is the time rate of change of angular momentum. And so essentially, the way you should interpret a torque is that the magnitude of the torque is telling you the magnitude of the rate of change of angular momentum. So a 10 Newton meter torque is a torque that is changing the angular momentum of an object by 10 kilogram meters squared per second every second. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, now let's just make sure we have that relationship and that equation down pat. Let's go ahead and write that down. You can write this down under the heading torque and angular momentum. I'm not going to go and give you the symbol here because we've already defined all these symbols, at least at first. But when we're saying the torque is equal to the time rate of change of angular momentum, it's important to realize here, what we're saying is that the net torque is equal to delta L over T. And that means that's L final minus L initial over time. The final angular momentum minus the initial angular momentum over the time, where of course tau net is the net torque, delta L is the change in angular momentum, L with the subscript F is the final angular momentum, L naught is the initial angular momentum, and of course T stands for the time. This, in the angular momentum unit, especially in the AP Physics 1 course, was like a super important equation. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now I think this animation here is really interesting because of the way it shows you the relationship between torque and angular momentum. And so there are just a couple things I want to comment on. The first thing I want to comment on is it's pretty interesting here that they show you L is R times the momentum, because remember, we said most of the time the rotational variable is that linear variable times R. And that actually holds up for both of these vectors here. So the first thing we should say is the angular momentum vector is shown by this light green arrow. And so notice when this thing is moving counterclockwise, its velocity vector is being shown here as counterclockwise, and the momentum vector, the angular momentum vector, is up. Notice right-hand rule, curve it in the direction of rotation, thumb points up. But when it goes clockwise, if we curl our finger in the direction of rotation, our thumb goes down. Additionally, here you can see that the force that's acting on the object is shown here in blue. And so when it opposes the linear momentum of the object, like it does here, it slows the object down. And when it acts in the direction of the object's momentum, it speeds it up. Notice the torque is basically functioning the same way. When the torque is in the direction, the angular momentum increases. And when the torque is opposite the direction of the angular momentum decreases. All of those old relationships hold up. And that's really important. Now, of course, the name of the game here is going to be, how can we use all this stuff to solve a problem? And so let's go ahead and solve the problem. It says here, what is the angular momentum of a 2.8 kilogram uniform cylindrical grinding wheel with a radius of 18 centimeters when it's rotating at 1,500 revolutions per minute? And then part B asks, how much torque is required to stop it in 6 seconds? All right, let's just ignore B for a second and focus on part A. So part A is asking us, what is the angular momentum of the 2.8 kilogram uniform cylindrical grinding wheel with a radius of 18 centimeters? So the first thing we should recognize here is that we are being given the mass and the radius and an omega. And we are also being given here that this object is cylindrical. And that means we need to use the equation for the moment of inertia of a cylinder. And just in case you forgot, the moment of inertia of a cylinder is given by the equation 1/2 mr squared. If I just wrote that down and you were thinking, wait a second, isn't that the rotational inertia of a disk? They have the same equation. A cylinder is a disk. So obviously, the first thing we're going to need to do when we're solving these problems is write down the knowns. The mass here is 2.8 kilograms. We have the radius of this cylindrical grinding wheel is 18 centimeters, so that would be 0.18 meters. They tell us here that the angular velocity of this object is 1,500 RPMs. And of course, when you multiply that by 2 pi over 60, you can convert it to radians per second. And when you do that, at least to 2 significant digits, you get 160 radians per second. And here we're looking for the angular momentum, L. So obviously we start here by using the equation L equals I omega. That's our equation. And now we have to recognize the fact, I know I wrote it on the last slide, but I'm just going to write it over here too, that because this thing is a cylinder, it gets the equation 1/2 mr squared for its rotational inertia. And so we need to rewrite that equation by subbing in the rotational inertia for the cylinder. Now, obviously, you can calculate that separately if you want to. I personally think that's a little insane, but whatever, you can go for it. And all we really have to do here now is plug these variables in. We have 1/2 times 2.8 kilograms times r squared, which is 0.18 meters, whole thing squared. I'm going to actually just put this whole thing in parentheses. And then we have to multiply that by omega, which is 160 radians per second. And we've got our rotational inertia. We've got our angular momentum. We're in business here, or sorry, our angular velocity. And so now to calculate our angular momentum, we just need to multiply those numbers. And when you do that math, you get 7.2576 kilogram meters squared per second, or to 2 significant figures, 7.3 kilogram meter squared per second. And that's it for part A. Let's go ahead and put that in a box and move on. For part B, they told us here that we need to find the torque when the object is being stopped in 6 seconds. So the first thing that we should say is for part B, we're going to have to calculate the torque. I'll write here net torque. And we are being told that the time here is 6 seconds. What you should also definitely realize is that when this object is moving, in other words, before it stops, that's what its angular momentum is. So it has an initial angular momentum of 7.3 kilogram meter squared per second. And the final angular momentum, when the thing is stopped, is going to be 0, because this thing isn't rotating anymore. And now we have every single thing that we need to solve for the torque, because we already said so far the torque is equal to the change in angular momentum over time. And that means that's the final angular momentum minus the initial angular momentum over the time. And so the net torque here is going to be L final 0 kilogram meter squared per second minus the initial angular momentum 7.3 kilogram meter squared per second. And we're going to divide that by the time, 6.0 seconds. And so we should get a torque here that's just over 1. And of course, when you do that math, you get negative 1.2 Newton meters. Now, it should be noted, I think, that the torque is negative. And it makes a lot of sense, at least to me, that the torque is negative. The torque is being used to stop the object. So, of course, the torque should be in the opposite direction of the angular momentum, because that ultimately is why the object is slowing down. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so I think hopefully what you saw from that problem-solving activity there is that solving for the angular momentum of an object is not really all that hard. Obviously, there are going to be some major differences in a lot of these problems. Some of them will be cylinders, some of them will be spheres, some of them will be hollow spheres, some of them will just be hoops, like whatever. Really, the only thing that changes is the equation you're going to plug in for the rotational inertia. However, there is a possibility, and we're going to talk about this now and basically for the rest of the video, that you have to deal with finding the angular momentum of a point mass. Now, a point mass is an object that has all of its mass basically located at one point in space. And finding the angular momentum of an object like this can be tricky, because mostly what we've been talking about in this rotational motion unit is what we call extended bodies. In other words, objects that have their mass distributed throughout a certain point in space, like this cylinder in this problem. It's got all of its mass distributed over that 18 centimeter radius, or really the 0.36 meter diameter. So let's go ahead very carefully then and define what a point mass is, how it works, and ultimately how we deal with angular momentum calculations for these things, because it could get tricky. So the first thing we'll say is that it's a little weird that we're going to be talking about a point mass having an angular velocity. And there's a good reason for that, because we're saying a point mass is defined as an object which has all of its mass concentrated at one point. And so what's particularly weird about thinking about their angular velocities is that these objects will not be rotating themselves, but rather they'll be revolving around a central point. Now, that's kind of weird, because when we're talking about angular velocity, usually we're talking about an object that's physically rotating. It's turning. That's not necessarily the case. These objects will be revolving around a central point, or in other words, they'll be experiencing circular motion. However, due to the fact that these objects will be experiencing circular motion, they'll technically have an angular velocity with respect to some rotational axis. Now, oftentimes in various years that I've taught this course, few people have found this confusing. I find that to be a little weird, because what we definitely talked about when we were talking about these linear to rotational translations is that, like, if a disk has an angular velocity, a point on that disk, because it is experiencing circular motion, has a linear velocity, and we can convert the angular velocity of the rotating object to a linear velocity for that point. Essentially, what we're doing here is just the reverse of that. We're going to be looking at an object that is not connected to a rotating object and basically just mathematically treating it as though it was a part of a rotating object. That's the idea. We're going to calculate its angular velocity it's not actually rotating. We're essentially, just for mathematical purposes, treating it as though it is part of an object which is rotating, because it fits in with everything that we're saying here about angular velocity. And so the point is, since these objects have an angular velocity with respect to the center of the circular path they're traveling in, they've got an angular momentum too. And we can do a lot of interesting stuff when we consider the angular momentum of an object that's moving in a circle. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, what's particularly odd, in my view, about talking about the angular momentum of a point mass is the answer to the question, well, what the hell do you put in the equation for the rotational inertia? When we've been talking about rotational inertia, we've been talking about objects which have their masses spread out over some area of space. Now, here, when we're talking about a point mass, the most typical examples of point masses we're talking about are like a ball tied to a string or a planet moving in an orbit. And the idea is, within this orbit, like let's just say this is the sun, and this is the path of the planet in orbit, its mass is not distributed uniformly or otherwise throughout the distance between the sun and the planet. All the mass is over here. There's actually no mass between the location of the planet and the location of the sun. That should be a giveaway, though. Have we ever seen the rotational inertia for an object which has no mass in between where the stuff is located and the rotational axis? It's all on the outside. Can you say hoop? There it is. It's a hoop. Since all of the object's mass is concentrated as far as possible from the pivot point, a distance equal to the full radius of the circle, the rotational inertia equation will look like that of a hoop. All of the mass is concentrated as far as it can possibly be from the pivot point, just like a hoop. And so the point is, if we think back to that first day I introduced the concept of rotational inertia, when I use the equation I equals the sum of the mr squareds, you take all of the mr squares and you add them together. Well, for a point mass, there's nothing to add together. You just take that mass times r, and then you square it. And so the rotational inertia equation for the point mass is just going to be mr squared. This does not seem that important right now, maybe to some of you. When it comes to conservation of angular momentum, which is clearly coming up next, it's really important. So take a second to pause this video here and write that down, and then we'll actually go ahead and expand fully on that equation here on the next slide. So, of course, the rotational inertia for the point mass is going to be given by the symbol I, like every other rotational inertia equation. The equation, as we just mentioned, is mr squared, where m is the mass of the object, r is the radius of the circular path, and of course, I is the rotational inertia in kilogram meters squared. And so, of course, that's the unit. This is really, really, really important. Please take a moment to write this down, and when you hit play, we'll move on. All right, so the obvious question here is like, well, wait a second. Why are we talking about the rotational inertia of a point mass now? Because the whole point of this is we wanted to talk about the angular momentum of the point mass. And so the idea is, if we want to find the angular momentum of the point mass, given by the equation I omega, then we need an equation for its rotational inertia. And now we have one. I is equal to mr squared. Additionally, we said here that we are mathematically treating this object, which is just going to be moving with some linear velocity tangent to the circle, as though it was part of a rotating object. And when we were doing that, we were saying the relationship between the linear velocity and the angular velocity of a rotating object, like when we were actually considering the point of a rotating object, we were saying that relationship was v equals r omega. And so that means if we solve this for omega, we were doing this a lot for the ramp rolling, right? We get the omega equals v over r. So we have omega equals v over r. And plugging both of those things into the equation we have up there gives us L equals I, which is mr squared, times omega, which is v over r. And it cancels. And so what we end up with is a nice, neat, tidy little equation. L equals mrv. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so I want to formally introduce this equation because this is really, really super important. Obviously, the angular momentum of a point mass is important because, like I said, one of the more common examples of a point mass is a planet in orbit. And we're obviously coming back to those before the end of the year. So it's really important that we have that down. Now, the first thing we'll say then is that, of course, the symbol for the angular momentum of this point mass is going to be L, and the equation is mRV. This is not in the reference table. So this is something you're going to want to remember. Now, of course, you could always derive it. Honestly, the way I always remember it is because when I look at that, the first thing I think of is Marvin. I don't know why. But over the years, that's just always something that I've used to remember this equation. It's just like that idiotic thing. I think the fact that it is so stupid is what helps me remember it. But that's the idea. The angular momentum, Marvin. So m, of course, is the mass of the object. V is the velocity of the object. And r is the radius of the circular path. So this, let's be clear with a little drawing, is the angular momentum of an object with a mass of m moving with a velocity v that is some distance from the pivot point. That's the idea. L is the angular momentum given in kilogram meters squared per second. That's the unit. And of course, just like angular momentum for an object that's not a point mass, it's a vector. Take a second to pause this video here and write that down. And when you hit play, we'll use that equation to solve a problem. Okay, so let's take a look at one problem here before we go. It says here, what is the angular momentum of a 0.210 kilogram ball rotating on the end of a thin string in a circle of radius 1.10 meters at a speed of 11.4 meters per second? This is a pretty simple plugin. That said, I do want you to know how this works, and so I just want to show you this very quickly. So they tell us here that the mass of this object, the mass of this ball, is 0.210 kilograms. They tell us that it is traveling in a radius of 1.10 meters, and we are told that the speed of this thing is 11.4 meters per second. Like I said, this is about as simple of a plugin as you can get. The angular momentum is Marvin, MRV, and I do want to be clear, when you are using this equation, you don't need to write down the other version. You could just go straight to MRV if you recognize it's a point mass. So we have the angular momentum is MRV, and so we have the mass, 0.210 kilograms, times the radius, 1.10 meters, times the speed, 11.4 meters per second, and you just multiply three numbers together. When you do that, you get 2.6334 kilogram meters squared per second, and we'll just go ahead and round that off to 3 digits. We'll call it 2.63 kilogram meters squared per second. Cool. Take a second to pause this video here and write that down, and when you hit play, we'll wrap it up for today. Okay, and now for something completely similar. It's important to realize this problem that I'm about to show you is very similar. It is not identical. That is the first and most important thing for you to notice about it. This problem here says, what is the angular momentum of a 0.270 kilogram ball revolving on the end of a thin string in a circle of radius 1.35 meters at an angular speed of 10.4 radians per second? I like this question because this question kind of mixes flavors, if you will, from both equations, L equals I omega and L equals MRV. And so what I want you to do today to submit is show the work for this calculation using both of the equations for angular momentum that we developed today. Do it one way, do it the other way, and that's your work to submit for the day. And with that, that'll be it for the week. All right, everybody. Have a good one.